Here we are going to integrate the function y squared plus z squared over a region which is a cube of side 1, with one corner of the cube at the origin and the sides of the cube along the x, y and z axes. So we are going to take each point in this region, evaluate the function y squared plus z squared. In general, this will be a function of x, y and z. Now this particular function does not involve x, but often it will involve x. But anyway, we'd have to plug in for y, plug in for z, evaluate this thing, and multiply it by a tiny volume element. Now I could have shown the point at the center of a volume element, but it doesn't actually matter, because when we take limits it will all work out to be the same, whether the point is at the corner of the volume element or at the center of the volume element. Now we start by considering a volume element of volume delta V, so we haven't taken limits yet. The distance shown here along the top of the box is delta y. This edge here has length delta z, and finally this edge here has length delta x. So the volume delta V of the box is got by multiplying the three sides together, delta x by delta y by delta z. So we have to evaluate the function at a point inside the box or on one of the corners, it doesn't matter because we'll be taking limits, and multiply the value of the function at a point in the box by the volume of the box, and then we have to sum. We have to do that for every point in the region and then sum all those products. So in this first picture we could imagine that we have calculated the product of the value of the function at the point x, y, z and the volume element delta x, delta y, delta z. Okay, so that's all we've done here for this first picture. Now this is only an approximation, of course, because we haven't taken limits. We haven't let delta v go to 0. In other words, delta x, delta y and delta z must tend to 0. But before we do that, before we take limits, we have evaluated the function, if you like, over this tiny volume element delta v. Next we can consider a column here, a vertical column actually, running from z equals 0 to z equals 1. All points in the bottom face of the box have z value 0, so we could take a general point x, y at the bottom face of the box, its z value is 0, and consider a point directly above it. That point will have coordinates x, y, 1. The x and y coordinates will be the same as this point because it's directly above it. Now we could consider doing what we did in the first part for all volume elements ranging from z equals 0 up as far as z equals 1. So we could have considered a volume element down here, and we could have calculated this quantity here for the volume element down here. In this case z would be 0, we'd be plugging 0 in for z, and y would be whatever, because y is a general point. Okay, x and y are general, well, as long as they're points anywhere in the bottom face of the region. Okay, and we could consider doing this calculation, then repeating for the next value of z, a tiny increment upwards and so on, and keep doing that until we get to z equals 1. So then we would have to sum these quantities from z equals 0 to z equals 1. We would have a finite number of quantities because we haven't taken limits yet. So this would be some finite sum. It would depend, of course, on the size of delta z, the size of the increment. Next, we are going to get the value of the function y squared plus z squared over this region shown here. Now, the height of this pillar here depends on y. For different values of y, we will have different pillars. Like we could have kept x fixed. Okay, so we imagine we're keeping x fixed here for the purposes of this particular setup. Say y was this point here, we would have a different pillar. Okay, so as y varies, we have different pillars. Z is fixed actually. Well, I'm sorry, Z is runs from 0 to 1, but of course we can vary y. Y can run from 0 to 1. So we can imagine summing all these pillars from y equals 0 to y equals 1. That means we get this double sum. So now we have evaluated the function y squared plus z squared over this slice. And that in general will depend on what x is. We could have taken a different slice at a different position. So we need to consider all such slices running from x equals 0 to x equals 1. So we just need to sum the double sum from x equals 0 to x equals 1, and we will have evaluated the function y squared plus z squared over the entire region. Now let's take limits as delta x, delta y and delta z go to 0. So in this case our volume element delta v becomes dv. So our triple sum will become this volume integral here, the integral of y squared plus z squared dv over the entire volume v. Okay, v is the entire region. What we can do is we can replace these summation signs with integral signs. So instead of summing from x equals 0 to x equals 1, we are integrating from x equals 0 to x equals 1, and the deltas are replaced with d's. So it can be shown that this triple sum becomes what's called a triple integral. Let's evaluate this triple integral. Now we do this like we do double integrals. We start out with this inner integral. We are integrating y squared plus z squared with respect to x, so y and z are treated as constants. So that's going to give us y squared x plus z squared x, or I could just write y squared plus z squared times x. X equals 0 to x equals 1. Well, that's going to give us y squared plus z squared. So we integrate it with respect to x, so x should not appear in our answer. We should get a function of y and z only. Okay, next we take the second integral. We're integrating the thing in red with respect to y. Now, the result of the innermost integral was y squared plus z squared. If we plug 1 in for x, we get y squared plus z squared. So that has to go in here. Just happens to be the same as this. That's just a coincidence for the particular function and the limits that we're dealing with. Okay, so we are integrating this with respect to y. If we integrate y squared with respect to y, we get a third y cubed. Now z squared is treated as a constant, so we get z squared y, and our limits are from y equals 0 to y equals 1. So if we plug 1 in for y, we get a third plus z squared. Then we have a minus sign. If we plug 0 in for y, we get 0, so we can forget about that. Finally, we have the outermost integral, and we have to integrate the result of the previous part, the third plus z squared, with respect to z. So from this we get a third plus a third, which is 2/3. Now, suppose that the function that we were integrating was not y squared plus z squared, but was just 1. So, for each point in the region, the value of the function is just a constant, it's just 1. So for x, y, z, the value of the function is 1, no matter where x, y, z is in the region. And we have to multiply the value of the function, which is 1, by the volume element dv. And then we have to sum all those volume elements. But you can see that this will give us nothing other than the total volume. So if the function that we're integrating is equal to 1, the constant function 1 for all points in the region, then the integral of it with respect to v is the volume of the entire region. So let's use the triple integral to get the volume of the cube of side 1. Well, we know what the answer is. we know how to get the volume of a cube of side 1, but let's just use triple integration to do that. So I'm letting the letter V to stand for the region, but the volume of the region is 1 multiplied by 1 multiplied by 1, which is 1. Okay, so let's take the innermost integral. So we want to integrate 1 with respect to x. Well, that's just 1x. And the limits are from 0 to 1. So if we plug 1 in for x, we get 1. So the innermost integral has a value of 1. Okay, so this next integral is from 0 to 1, and we have to integrate the result of the innermost integral, which is 1. But this time we integrate with respect to y. And if we integrate 1 with respect to y, we get 1y, and the limits are from 0 to 1. If we plug those limits in, we get 1. Finally, we have the outermost integral. It's an integral from 0 to 1. We want to integrate the result of the previous part, which is 1, but this time we integrate with respect to z. If we do that, we get z, and our limits are from 0 to 1. If we plug in our limits, we get 1. So here's the final answer. This is the volume of the region. In later videos we will cover more complicated volumes. This one was very easy to work out without triple integration. But the key thing is that when we're getting a volume, we're integrating 1. And here the limits are very easy to deal with. But in general, of course, we will have shapes that are not as simple as cubes. And the limits here will make things more complicated.